Hi, everybody. I'm Adam Jones, and as he said, I'm here to talk to you about orientation perception. And I want to call out my co-authors here, Jonathan Harper, Mark Bolas, and David Krum. Without their help, this paper and the study wouldn't have been possible. Okay, so a little bit about the motivation behind what we were doing. This began as part of a larger project that was examining how people perceive spatial relationships under different field of view viewing conditions. As has been pointed out numerous times in this one session, which, that should tell you how true it is, there's lots and lots and lots of distance judgment work, both in the real world and in VR. And there's a decent amount of environmental orientation and wayfinding work. I don't know if Bernard Rique's here this time around, but a lot of that is his, and he does some excellent orientation work. But interestingly, very little work has been done examining object orientation, so orientation of objects within the environment around you, not so much wayfinding or orienteering. And so when we talk about orientation during this talk, we're going to be talking about it specifically in the context of what we call allocentric orientations along the ground plane. So angular relationships between objects located on the ground outside of the observer. There hasn't been a lot of work just in general looking at this, especially with regard to 3D computer graphics. The earliest one, or really the only one that we're aware of, is by Tharp and Ellis. In the 80s, they were interested in air traffic control tasks and how well observers could judge angles between two objects rendered on a perspective view on a 2D screen. And what they found was that people are bad at it, like really bad, but they are consistently and systematically bad. They specifically, yeah, that's wonderful. That's really great, especially if you want to model it. So this awesome badness followed a sinusoidal pattern for pretty much every participant that they ran. And we're interested on whether or not this occurred in virtual environments too. In one of their follow-ups, they seem to show that the errors resolved in a similar real-world task, and we'll loop back to that comment in a minute. So first, we're going to talk about experiments 1 and 2 together. Spoiler alert, there wasn't much of a difference. But experiment 1 was doing a task similar to what Tharp and Ellis described with their air traffic control task. We had objects on the ground, a red reference sphere that never moved, and a green target sphere that moved to orbital locations around the red sphere. And then using the Tharp and Ellis clock-like widget, subjects would indicate the angle that they believed the target object was relative to the reference object, relative to their forward view. Now, the difference between experiment 1 and experiment 2 was field of view. In experiment 1, we tested a common 60-degree field of view. So the field of view you'd see in pretty much every HMD used in research in the early to mid-2000s. And for the experiment 2, we tested the full field of view of the Wide 5 display. Well, almost the full field of view. It has a 150-degree field of view, but naturally you want to be sure you've calibrated any errors out of your display, and we used a fisheye camera to do that, and we could only reliably calibrate the central 138. So everything outside 138 was rendered black. In these experiments, we had a total of 20 subjects. We tested 18 stimulus orientations, 360 degrees and 20-degree increments. Each stimulus was repeated 3 times and was counterbalanced using a restricted random shuffle, resulting in 1,080 total measurements. Now, a little bit about the analysis procedures that we used. Most of the analysis techniques that we typically see in spatial judgments, especially in our field, are linear and based on a normal distribution. That's not going to work for directional data, unfortunately. So you have to do special directional statistics that adhere to the directional version of a normal distribution called a von Mises distribution. We specifically used a Watson's U-squared test, which we used to essentially determine whether a statistically significant portion of our samples fell to one side or another of a reference. And we also computed 99% confidence angles, and that one's kind of obvious what it is. Not going to go over this for the rest of the experiments because they essentially follow the same pattern. So here's the results that we found. Beautiful, beautiful sinusoidal patterns. This is some of the most beautiful data I've ever collected. I want to frame it and put it on the wall. But what we found was exactly what Tharp and Ellis had found back in the early 90s, that people exhibited a pattern of sinusoidal error with very low error towards the cardinal directions and very high error along the diagonals. What we were kind of surprised to find was that the pattern didn't change at all for the very, very large field of view condition. And not just large field of view, but this specific field of view, this specific display in this specific environment has been shown to cause perceived changes in scale. And we'd expect to see at least a change in error magnitude if that was happening here too, but we don't see it. So could this be a property, and especially since Ellis and Tharp reported that the error disappeared, or didn't disappear, changed in the real world, could this be an artifact of looking at 3D computer graphics? Let's test this in the real world and find out. So we replicated the procedure as best we could in the real world. So we had spherical balloons placed at the same distances from the observer as they were in the virtual environment. We had a widget mounted on an arm, positioned in the same location in the person's visual field as the widget was in the virtual environment. The resolution of the display was scaled to match the resolution of the head mount, and the angle subtended by the widget matched that of the head mount. So we got everything as close as we possibly could. One thing we couldn't do, though, is instantaneously teleport stimuli from one position to the next. So one important difference is that in between trials, we asked the participants to close their eyes briefly while an experimenter ran out there and very quickly moved little balloons around. We had them weighted with marbles so they wouldn't float away. That was actually quite a problem in pilot testing. So the results that we found look something like this. The strong pattern of sinusoidal error isn't there. So obviously, it was the result of computer graphics. Yeah, you don't want to take a picture of this slide. Wait to the next one. Because I'm being sarcastic right now. Obviously, it was a result of viewing in VR. Well, not so fast. Never just look at your average data, look at your individual subjects. And when we looked at our individual subjects, we saw a striking pattern. There were two profiles present. Exactly half of our participants exhibited the sinusoidal pattern we had seen. The other half also exhibited a sinusoidal pattern, but with a longer period. And this was visible in the data, but we have to quantify this, so we classified them using a fast Fourier transform classification method. So participants fell into the long group if their errors had a peak frequency of 1 hertz, and the short group if they had a peak frequency of 2 hertz. And similar to in our previous data, errors were very low in the short period near the cardinal directions and high along the diagonals. While in the long period, it was only near 0 along the vertical axes, which was interesting. Now, we're not really sure why that was the case. And we've got some speculation in a moment, though. But this could, I'm not convinced, but could imply that there are multiple strategies used for judging orientations, with one of them being more strongly preferred in the context of a virtual environment. But it's also possible that this was the result of the task itself. I'm very suspicious of having the participants close their eyes between the trials and the possibility that they could have mistook which sphere was the reference and which was the target in between. And some participants actually made a comment along those lines in debriefing. But if you modeled the kind of error you should see if that was happening, it doesn't look like a long period sine wave, which in itself is a bit curious. There was also a possible confound in our previous experiments, and that had to do with where you were conducting your observation and where you were reporting your judgment. So you're making your observation on a perspective plane, the ground plane, but then you're reporting that in a frontal plane. So is it possible that the internal transformation between perspective to frontal is what's resulting in this pattern of error? Now, if you do model this, you get, guess what? A short period sine wave. The magnitude's not right, but you do get a sinusoidal pattern. So that in itself is somewhat suspicious. Our solution was to introduce a new task, an angular bisection task. So you're conducting your judgment and observations not just on the same plane, but in the same object. So we had a projector out in the world that would project a 90-degree angle on the ground, and the participants would control a third arm that they then used to bisect that angle into two equal 45-degree slices. The projectors were calibrated such that we could switch between giving a presentation that would be frontally oriented on the ground or perspective oriented, as if the circle, was painted on the ground itself. So again, to give you an idea of what responses to different orientations would look like, it's something like this. Very similar, it's just the total angle in the field of view subtended by the lines changes between the frontal and perspective views. Now, the results for this, an even more finely tuned sine wave in the perspective condition, following exactly the same patterns we'd seen before. High error along the diagonals, low error along the cardinal directions. Now, what's interesting is when we looked at the frontally oriented stimuli, 12 of the 20 target orientations, their judgments fell within their 99% confidence angles. And 17 of the 20 were within 5% of the actual target orientation. So this is interesting. This is beginning to imply that it potentially is a transformation between the frontal and perspective planes. So that when we're judging orientations along the ground plane, and I appreciate the use of the term anisotropy earlier, because this is potentially a radial anisotropy along perspective planes. So judgment errors in the frontal plane appear to be fairly low. Now, another interesting thing here is that the errors start to peak around 90 degrees down to 180. If you perceive the center of the circle to be centered with its intersection point on the ground, those would be subsurface points. And it could be that you're having X-ray vision kind of effects like we've seen in some augmented reality studies, with the stimuli being perceived as being pulled towards the surface. Now, bit of discussion. FOV had no appreciable effect at all. It was actually quite surprising that we didn't see it. There's the possibility, though I am suspicious of this, that the observers could have two strategies for figuring out orientations, one more strongly preferred in the virtual world. Want to do a follow-up, and I think the eye closing might have something to do with this. Yeah, we may tend to judge orientations, regardless of their perspective, as if they're frontally oriented. And that will, if you do the math, will result in a sinusoidal pattern. But the interesting thing is, why would the magnitudes be different? There's always something to study. But the cool thing is that these very, very bad errors are very, very predictable, and they're very consistent from one participant to the next, which means they're highly modelable, predictable, and could potentially be incorporated into user interface elements where you're either wanting to accurately present or accurately record angular or rotary judgments. Okay, so that went like 20 minutes every time I practice it, so at 13 minutes I'm proud. And plus I'm the last one. What have you got to do today, really? Okay, so we'll call it there. Questions?
Very cool work. You always seem to think of everything and do like 20 experiments.
Thank you, Hedges. I appreciate it.
So first, just your thoughts on, like, it seemed like the error bars, sometimes they weren't even visible. They were smaller than the radius of the dot. So very low variance. People are really consistent, always, almost always.
Exceptionally consistent, like shockingly consistent. I say I want to frame this mostly because of how darn tiny those error bars are. I was actually surprised that they got even smaller when we went to the bisection task. They were able to home in more precisely than they were with the clock widget. Now that could be an effect of the resolution of the screen, because we did keep the resolution of the clock widget consistent between the real world condition and the HMD, and the HMD was somewhat low resolution. So it could have, the larger error bars there could have been a result of just screen resolution, but really tight nonetheless.
Yeah. The other question is regarding the real world, especially with the balloons.
Yes.
It seems that, at least from the picture, there is a checkered, somewhat of a checkered pattern on the floor.
Yep.
Do you think that could have, impacted somehow with guidelines and such?
Potentially. I'm actually glad you mentioned that. It's a good catch. We thought about that, and if the grid was aligned with a person's view, that would definitely be a forward reference that they could exploit. And other work by Ellis looking at orientation judgments have shown that does help people significantly. So we actually rotated the observer such that they weren't on axis. They were about 22 degrees off axis from the grid.
Cool. Yeah. See, you think of everything.
So you may have mentioned this, and I just missed it in the methodology, but the field of view restriction, was that done symmetrically in terms of its aspect ratio, or did you just horizontal, vertical?
So also a very good question. We were specifically mimicking the field of view that you would see in the SX or in-visor SX or ST60. So since that was a very, very common, especially when this data was collected, very common field of view in use in research. So it had a 4:3 ratio.
Okay. Have you thought about potentially restricting the vertical field of view, but particularly the lower field of view, because that would potentially disrupt your mapping or your ability to perceive the perspective along the ground plane?
So for orientation judgments, no. For distance judgments, yes. I think it was last year, might have been the year before. We've got a paper in Transactions on Applied Perception looking at the effect of vertical field of view extension on distance judgments. And lower field of view is very important for accurate distance judgments. Upper field of view, not so much, and that makes sense. But it wouldn't surprise me if there would be an effect, especially since we saw one there. But then again, I would also not have been surprised if field of view had an effect on this at all, and it turns out not to. So who knows? We'll see.
Thanks.
Thank you very much. I agree, there has been very limited work on the orientation study. I was just curious, because if you're thinking about the pointing as well as the gaze direction, they are also an indicator of the orientation, right? I was just curious whether there are any similarity pattern, like the sine wave, known for the gaze or pointing direction in general with this study.
So we didn't look at any pointing. The gaze direction was used as a reference for the first 3 experiments. And I don't know, and someone else, you're welcome to volunteer if you do, know if there's been any egocentric orientation kind of, And I see Janine shaking her head, yes. So yeah, she knows. But I not in terms of allocentric judgments, no.
Okay, thank you.
You're welcome.
I absolutely love your study, and particularly like the fact that you actually did go and look at the individual data, not just the collective data.
Thank you.
Got a couple of quick observations,
Yeah.
and that is that yourself, along with some of the other presenters today as well, it's quite common to be using spheres or balloons. It raises a concern for me because spheres and balloons have no changes in external angles, no change on internal angles or any other cues. And so that does worry me. I don't think it will detract from your results at all.
Oh, yeah.
But I'm just kind of curious, if you did put those other richer cues in, would it actually modify the results or change the sinusoidal wave?
I kind of think it would. So especially if you used cubes, the stimulus itself ends up being a spatial directional reference because you've got those nice sharp corners. And if we look back at my recreation of and this is as close, I couldn't find any photos. I had photos of their real world experiment, but not their virtual. This is from their description, the best I could get. They did use cubes, but in rendering a sphere back then was computationally intense. So their solution here, they didn't want the cube to act as a reference. So it was rotating randomly, and so it couldn't be a consistent directional reference. So yeah, we were trying to avoid that, but I do think it could potentially have an effect.
We've been using icosahedrons. They give much richer depth cues,
Oh.
and they're much easier to perceive exactly where they are in space. But we've been using it in a health context, not at IEEE.
Yeah.
The other thing I want to say is there are also some publications, funnily enough, originally coming from air traffic control, about the red and green, because red is also perceived at a different distance than green is.
That is
So
true. That
just
is
to
true.
raise that as well for you.
Yeah.
But thank you very much indeed. A really interesting study.
Ah, thank you. Thank you. And just following up with that, after we started collecting data, I was like, red and green's a bad idea. But we'd already started, it's like, well, we're going to roll with it. Anyway, thank you very much.